Hello everybody. In chapter 18.6 we will look at electric fields. So let's start with a small experiment. Here it is dark on purpose and you see a so-called Tesla generator here. And if it is plugged in, it makes some noise, but you actually can't see anything. So what is this object doing? It might be more obvious if we take a fluorescent lamp. So you might have one of these at home and bring it closer to this Tesla generator. So I'm holding it in my hand as you see here. And let's now see what happens if I go closer to it. And you see clearly that the environment of this generator is, as we called, an electric field. So in the environment here, we do have some electrical properties caused by this machine. So let's, in a more general way, look at fields. We can, for example, here have a look at the sun and the earth. So we are looking at gravity, or also the so-called gravity field. As we know, the earth circles the sun. Why is it? Well, the reason is gravity. The earth is attracted by a force. What happens if the sun disappears? What will the earth do? Of course, it will then follow a straight line. But at what time will the earth be following this straight line? The answer is, if the sun disappears, the earth will still circle the sun for roughly 8 minutes, and only then it will continue on a straight path. So even though the sun is not there anymore, the earth just feels the strength, some sort of the sun. So the sun is the, as we call it, the source. And this source sends out here a gravitational field to all directions in space. So we have the G field, and the earth is reacting to this field, so we have a force. Same thing now is true with electric fields. We have a certain source here given, which in this case is a, for example, positive charge. This charge is sending out an electric field to all directions. And if we place another charge here, let's call that Q0, this charge will here positive, so it will be repelling, experience a force to the side here. So again, we have the source, then we have the electric field, some sort of in between, and as a result we have the force. In the experiment we have seen that this fluorescent lamp was some sort of feeling the electric field. And in everyday life we want to know, for example, what is the electric field at this position, for example here at this spot. So what we could do is we take a small charge. Let's take here a small positive charge, which we call Q0, and we observe what the charge is doing. For example, the charge might be pulled or pushed to the right side with a certain force F. Well, why is it pulled? There has to be an electric source somewhere. So it might be a negative charge over here, so it is attracted, but it also might be a positive charge on the left-hand side, so it is then repelled. We don't know. But what we can say is that at this position, the charge experiences a force to the right. This force depends on the source that we don't know, and of course it also depends on Q0. So for example, if we take a larger charge Q0 and place it there, we will experience a larger force. And therefore the definition of the electric field is given as force divided by the so-called test charge. And since the force has a direction, the electric field has a direction too, and the direction is the same as the force here. Unit will be here Newton per Coulomb. We can also write this down as a sentence. The electric field E at a certain point in space is given by the electrostatic force F experienced by a test charge Q0 divided by the charge itself. If we look at the picture, then we see the force that we have up here depends on the surrounding, so on this source charge that we do not see, but also on Q0, on the one hand by magnitude, but also it depends if it is a positive or a negative charge. For instance, if I placed a negative charge here, then the force is going to the left. Therefore, we also have to define what this test charge is, and the test charge is always defined to be positive and small, so it has no influence on other objects that are around. Let's make an example. So a charge, we take it as our test charge of 12 nanocoulomb, a positive one, experiences a force of 3 times 10 to the power of minus 3 Newton. What is the electric field? So the electric field is F over Q0. So the force that we have measured is 3 times 10 to the power of minus 3 Newton divided by 12 nanocoulomb, and the calculator then gives us 2.5 times 10 to the power of 5 Newton per Coulomb. The electric field E has a direction, and since Q0 is here positive, then the direction of E is the same as the one of F. So therefore, if we have now here our test charge, Q or Q0, and the force is pointing, for example, in this direction, F, then the electric field has the same direction as F. So it might look like that. Let's do a second example. So now we have a certain charge given, which is negative, and this charge is at a position where we have an electric field of 2.5 times 10 to the power of 5 Newton per Coulomb, which just is what we had for the upper one. So if we have an electric field given, then this electric field has to have a certain direction. So for example, if we are investigating on this point, then the electric field might look to that direction, E. So I just took the same as above. And then we can just take this definition of the electric field that we had up here. To get that, here it is. And then we rearrange it and resolve that for F. F is then Q times E. So F is then Q times E. So I'm not taking the test charge, but any charge here. And therefore, if here Q in our case is negative, minus 3 nanocoulomb, then the force will be to the other direction as E. And we can get the magnitude. We get a result of 7.5 times 10 to the power of minus 4 Newton. I have not written the negative sign, the minus, since a force always has a direction. So the negative sign just states that force and electric field are opposed to each other. So you can put the minus if you want, but it's not necessary because we can see the direction out of the drawing. As you can see, this value is 4 times less than what we had to start with, or what we started with at example 1. And this is quite clear, since the charge is 4 times less, then the force is 4 times less, and due to the minus, the direction is flipped.